on this computer. There we go. Okay, now share screen. So looking at number 4a, that one should be pretty quick. So they want you to write an equation of tangent line x equals 1. I mean, that one should be very, very straightforward. Y equals mx plus b, or you could also do this, right? And we kind of know that f of 1 is 15, so you can do y minus 15, x minus 1, and your slope is going to be the derivative, which of course is 8. So they're fine if you leave it like that. You don't really need to do much else with that one. Yeah, so that one should be pretty straightforward. Okay. Looking at, shoot, hold on a sec. Oh, there we go. Find the answer key here. Yeah, so anyway, and then you want to plug in 1.4 after that. We won't need to waste of time with that. Part B, we'll hold off on that one. I don't feel like doing that one right now. So, but I just wanted to, just kind of, because C and D are kind of closely tied to A. So let's look at C now. So for Euler's method, let me kind of show you a resource in case you guys forgot. And I'll send you guys these resources in a little bit. So here is how Euler's method would work. We kind of use it to help us approximate the value of a function at a certain x value. So if you look over here, this kind of looks like, and this is actually done, it's kind of like an equation of line if you think about it, right? But it's an iterative process where you're using it to approximate what you're actually looking for over here. So like you have a point that like this tangent line the curve has in common. This right here is going to be, t1 comma y1 is going to be like your approximation if you want to think of it that way. And this right here is obviously the real value. So yeah, I mean, we just kind of do that. But then what you do is you will kind of do it again using a different value. And you would kind of just keep going through this process until you've gone as far as you'd like to go. So if we look at this problem here, so they asked us to use those methods starting at x equals 1 on 2 steps of equal size. So we're going from 1 to 1.4. On 2 steps, so basically your delta x, if you want to think of it that way, is going to be 1.4 minus 1 over 2, or 0.4 over 2, which is just 0.2. So the way we're going to do this, we're going to start by saying f of 1.2 is going to equal f of 1 plus whatever our delta x is. Times f prime 1. Then we do it again. And we've actually already done this for 1.2. So it's an iterative process in a way. I mean, if you want to go back to what we see over here, so, T minus T1, T2 minus T1, T3 minus T2, T4 minus T3, it's just going to be the common difference. And then here we're just taking our derivative values, the base of the slope, right? So that's the derivative value. And then plus the y value that's associated with that derivative value. So going back to over here, if you work this out, f of 1 I know is 15 as it tells in the problem. Delta x is 0.2, and that prime 1 we know is 8 from the table. So you work that, you get 16.6. So now that's 16.6 over here. So that's why it's an iterative process. Then 0.2 times f prime 1.2, which is from the table here, is times 12. Work that out, and you should get 19. So it's a pretty straightforward process. So it's not really too bad. So while that's kind of fresh in your head, let's do this. Any questions so far about what I just did? No? Right. So while this is fresh in your head, I'm going to pull up the 2013 exam. And you're going to give this one a shot for part B in number 5. So 2 steps of equal size, you're going from 0 to 1/2. So your delta x is going to be 1/4. And you're going to be starting by finding f of 0.2. Then you'll do f of, 0.25. Yikes. Wow, I can't believe I did that. Hold on. Wait one sec. Yeah, I'm going to say f of 0.25. My bad. Yeah, because remember, f of 1/2 is the same thing as saying f of 0.5. So go ahead and work that out, and then tell me what you guys got. And feel free to use a calculator, because I don't think they're really going to check on the actual AP. You do round, by the way. You round to 3 decimal places, please. You can also give the answers a fraction, too. I'll work it out, just make sure we're in agreement. Okay, let's make sure we're in agreement. So when you do the first part, f of 0, of course, is -1 because they tell you that's an initial condition. Our delta x is going to be 1/4. Remember, we did two steps of equal size. We went from 0 to 1/2, so you're doing 1/4 as the change in x values. And then f prime is 0. You have the differential equation here. That is your derivative. That is how you're going to find f prime. And so you got to plug -1 for y and 0 for x. So you should get -0.5 if you do that correctly. Sorry, you should get 2 if you do that correctly for f prime is 0. So when you work it all out, you do get -0.5 for f of 0.25. So f of 0.25 is -0.5. Then you got to do it again. Remember, f of 0.25 is -0.5, so that's what we have over here, right? Delta x 1/4. And then this one's a doozy. F prime of 0.25, we're going to use this again for our derivative. So the y value of 0.25 was -0.5 as we established in the previous step. So you got to square that, so that's 0.25 times, and then you plug in 0.25 for x, that's 2x plus 2, that's going to be 2.5, I believe. So you're doing plus 1/4 times 1/4 times 5/2, and that's -1 out of 2. So if you continue working that out, I think that's -1/2, oh boy, plus 5 out of 32. So it's like saying -16 out of 32, so you should get -11 out of 32. It's a lot of just, I mean, again, use your calculator if you need to. It's just a lot of just crazy math there. Any questions about that Euler's method? No? Okay, cool. So now we're going to talk about Taylor series. Okay, for Taylor series, this is a pretty good resource. I like this resource a lot. That's essentially what you're trying to do right here. That's it. Or right here. And it just depends on whatever function you're dealing with. You take your derivative, then you do a second derivative, do a third derivative. And it's just a process you go through. Just want to make sure you can apply it. I have a suspicion they might make this a little bit more challenging, so I'll try to find more challenging Taylor series problems for the following 3 weeks. But just to kind of jog your memory, or if you guys just wrapped it up too, you know, maybe you guys just covered in your AP Calculus classes recently. So just show you how it's done. It's pretty straightforward. So look at 2012 again, and we'll look at number 4, part D. So you have to write second degree Taylor polynomial for f at x equals 1, and then use the approximate f of 1.4. So what you're going to do for that one, so you're going to start with f of a, and I'm going to kind of go back and forth here. So you want to start with f of a plus all this junk here. So plus f prime of a, or 1 factor, which is kind of redundant because I kind of know it's right 1, times x minus a to the 1 power plus f double prime of a over 2 factorial times x minus a squared. And you just kind of just keep going. until you get which one. Since you want second degree, that's as far as we need to go. So our A is 1. So you're going to do f of 1 plus f prime 1 over 1, of course, just 1 anyway, times x minus 1 plus f double prime, which they already give you, so we're okay there, over 2 factorial, which is 2, times x minus 1 squared. You can leave your answer, well, not quite, because you want to substitute, obviously. So f of 1 we know is 15 plus 8 times x minus 1. And then f double prime is 20. So 20 over 2, which is 10. So you have to do 20 over 2, which is 10. X minus 1 squared. If you leave your answer like that, it's totally fine. And actually, I'll give you 1 point for doing that polynomial correctly. Then you just got to plug in 1.4 into that. That's all.
If you left it as 20 over 2 factorial, would you lose
it's fine.
the
Yeah,
point for that?
It's fine. Yeah, because they don't really ask you to simplify. I do think you want to at least, yeah, I think they would give you, if you did 20 over 2 factorial, I think they give it to you. I'm pretty sure they would. And if you were to work that out, I think you get 19.8. So that's basically what you expect from a Taylor series. So pretty straightforward. Just check and make sure you guys know how to do it. So let me go ahead and clear all that. And I think we're going to do McLaurin just a little bit, but I want to do a Taylor from 2013. Yeah, we did already 23 number 5. Yeah, let's do. Yeah, let's go 2013 number 6. Okay, so now they're using some, they call P sub n of x, whatever. It's centered at x equals 0, fine. They do give you the derivative, so you kind of know how to work with that. But again, what you're trying to do here, if you want a third degree, so you're going to have to actually generate 4 terms actually for this one. Well, actually not really, because no, actually, yeah, we're generating 4 terms. That's right, yeah. So here's what we're going to do. Third degree, so we do P. So you're going to have to do this first. So you're definitely going to need f of 0 plus f prime of 0 over 1 factorial times x minus 0 to the 1 power plus f double prime of 0 over 2 factorial times x minus 0 squared plus f triple prime of 0 over 3 factorial times x minus 0 cubed. Good thing we made x centered around 0, because otherwise this would have been really nasty. And oh shoot, this is actually in terms of h. Darn it. Okay, fix this. It's totally arbitrary, but whatever, it's fine. There we go. But it is related to f, because h prime of x is f of 2x. So h prime is 0, f of 2 times 0, which is f of 0, which we kind of already know what that is from over here. So that should be pretty easy. But you're going to have to be really, really careful with h double prime of x is actually going to be f prime of 2x times the derivative of 2x. You got to do a chain rule. You have no choice but to do a chain. Okay, that's really messy. You have no choice but to do a chain rule here. And then when you do h triple prime of x, so you're basically doing f double prime of 2x. But in essence, really what you're doing, you're doing the derivative with respect to x of h double prime of x. So it's somewhat of an iterative process. So I'll have you guys try it, see what you get. So I'll give you guys a few minutes and we'll discuss. Then after that, we'll do a core series. 1 sec. Oh, shoot. It's kind of like brain surgery here. So hopefully the first term you're cool with, because they kind of tell you what it is anyway, like 7. H prime is 0, which we established is h prime of x is f of 2x, so that's just f of 0, which is -4. You're told that in part A. So you just use that information. So the first 2 terms you guys should be pretty easy. The third term, be really careful. And now you can do h double prime is 0. So h double prime of x is f prime of 2x, but with the chain rule, the derivative of 2x, of course, is 2. So h double prime of x is f of 2x times 2. Of course, x is 0. Sorry, it's f prime of x times 2. F prime of 2x times 2. Well, f prime of 0 is given to us over here, which is 2. And of course, times 2 is part of the chain rule, times x squared, and then divided by 2 factorial is part of the Taylor series. And then lastly, what you're looking at over here is you're doing the derivative of the second derivative, forget h triple prime of x. So if I want h triple prime of x, it's going to be f double prime of 2x. And you still have the 2 from before, and you got to do a chain rule. So this 2 is the 2 from before, and that 2 is part of the chain rule right here. So it becomes 4 f double prime of 2x. That's why I have the 2 times 2 there. F double prime of 0, because you're putting 0 for x, is 2, as we, is -2/3. And you divide by 3 factorial, which I know is 6, and you have x cubed. So if you clean it all up, you should get 7 minus 4x plus 2x squared, and it should be minus 8 over 3 divided by 6, which is minus 8 over 18 x cubed, or you make that 4/9. 7 minus 4x plus 2x squared minus 4/9 x cubed. Yeah, I mean, maybe we'll ask that, I don't know. So, I do know they got something about series, so I mean, I would be shocked if it didn't, because that's, a big reason of how that, big part of how that's different from the AV course. Any questions about that one? No? Okay. So lastly, we will now do Maclaurin series. Interestingly, the 2013 exam totally left it out. That was really interesting. Unless I'm missing it, maybe it was somewhere else, but I don't really. Yeah, that's kind of shocking. So anyway, let's look at number 6 from the 2012 exam. So this is kind of a quintessential Maclaurin series. If we look at Maclaurin series, that's kind of what your it's not that much different. In a Taylor series, but it's centered at x equals 0, so that's kind of what we're expecting. Or if we look at like another, yeah, here's kind of like another one. So yeah, so it's not that much different. But with some things that they will probably do, we'll have to maybe do the ratio test. So hopefully you remember how that works. So again, we're looking at 2012, one sec. No, it's 2013. Yeah. So they're asking to determine interval convergence from the Maclaurin series for G. So they did give you the Maclaurin series right here. So what you're going to want to do for the ratio test is you're going to want to do x to 2n plus 3 over 2n plus 5 divided by that you're replacing, when you get the second term here, essentially what you're doing is you're replacing n with n plus 1. That's how you get x to 2n plus 3, and that's how you get 2n plus 5 on the bottom. And you're simply dividing those two. So obviously the second fraction will flip. Now, you will need to be mindful of your exponent rules. So you can probably rearrange the fractions like this. Now, what happens over here? What does that reduce to? I know it looks a little nasty, but if you use your exponent properties carefully, what does that reduce to what I just circled? Anyone can chime in.
Is it x squared?
Good, yep. So you have 2n plus 3. Now, when you're asked to determine the interval of convergence, what you want to do is take the limit as n approaches infinity of that entire expression. If you work out that limit, what do you get? When n's approaching infinity, just using your experience with rational functions. What do you think this expression here would go towards if n's going towards infinity?
Three-fifths?
Just one. Remember, you're focusing on the leading terms. So you kind of ignore the 3 and the 5. So basically it'll be 1 times x squared or just x squared. So for example, if you were to graph like x cubed plus 1 over 3x cubed minus 4, if you took the limit as x approaches infinity, you just get 1/3. Because these degrees are the same. So we just get x squared for that one. Okay, so now what you're going to try to do is when you're doing the ratio test, you want, in order for it to converge, you have to be less than 1. Or you get that. So that's going to be your interval of convergence. So So that's kind of part of the ratio test. And we'll go over some other problems kind of like that, but that's what they're really looking for. They do want you to actually consider the endpoints. So if you were to plug in like -1 and 1, let's actually see what happens. So let's actually plug in the endpoints now. So you get -1/3 plus 1/5 minus 1/7 plus 1/9. And it's going to keep alternating signs. So would this converge? Yes or no? Are the signs alternating? Yeah, so we say that this converges. Alternative series test. Also, if I do x equals 1, I get 1/3 minus 1/5 plus 1/7 minus 1/9. Same reason. So truly, my interval of convergence actually is that. So when you're doing the ratio test, you're always going to take the original expression, and then go the next iteration for n plus 1, and then divide those two. So you do the higher minus the lower, or sorry, higher divided by lower. Do a little algebra, take the limit as n approaches infinity, and whatever you get has to be less than 1 for convergence. And then if you have endpoints to look at, you just plug them in and see what happens. And if they alternate, then we know that we're going to have convergence. So that's part A. Oh, let me plug my laptop. Let's actually take a look at C. I kind of care about that a little bit more. You're asked to write the first 3 non-zero terms of general term from a corner series of G prime of X. Okay. So let's do that. That one's actually pretty easy, but the general term's a little bit tougher. Okay, so let's look at C. Well, if you're doing G prime of X, you're essentially doing the derivative with respect to X of all this, because this is G, right? That's easy. You get 1/3 minus 3x squared over 5. That's 5x4 over 7. And those are your first, minus dot, dot, dot. Those will be your first 3 non-zero terms. The hard part's find the general term. So I suspect we'll still have -1 to the n. It's still alternating. That question mark is what we're kind of interested in. And remember, starting at n equals 0, so you're going to want to write something of this form. question mark here. So I'll give you guys a chance to kind of think about it. How do you think that should look? I mean, you could if you want. Take rid of that aspect x. So I'll give you guys a minute to kind of work that out. Okay, so hopefully you guys got this. Watch, what do you guys have? What would be your derivative here if you do the power rule? Where does that exponent go? To 2n plus 1.
Bring it down in front
Yep.
of that.
Yep. And then now x is raised to what power?
2n.
Perfect. Subtract by 1. So really, what's going to happen? It's going to be you still have -1 to the end because it's alternating. Plus it's like a constant, right? So that's a general term, which kind of makes sense, right? Because if you were to plug in 0, you would get 1/3. If you were to plug in 1, you would get -3x squared over 5. If you plug in 2, you will get 5 x4 over 7. You know? So yeah, it would make sense. So that's that one. Let me kind of show you for B really quickly. I do want to talk about L'Hopital's rule just a little bit, but these one of those kind of those odd questions that every once in a while they'll ask. So they say the approximate G of 1/2 using the first two non-zero terms of 17 over 20. So that'd be like these two terms here. And I guess it looks like what they did was they subtracted that from 17 over 20, 17 over 120. And if you were to plug 1/2 into the third term. I'm trying to understand what they did to the third term. You want to put this less than 1 out of 200. It seems as though whose terms in absolute decrease in absolute value to 0. Okay, I think I know what they did. Yeah, suppose that if you're adding the third term, that's only going to make this just a tad bit bigger. So that would be, I guess, a difference, because after that, it's just going to keep decreasing in value. So I think that's why they probably did that, to kind of just verify that that would be the actual difference between the true G1/2 value and the approximation. And if they actually were to compute this, that does become 1 out of 224, which is less than 1 out of 200. So I think this is, you're not really doing anything with the 17 or 120, supposedly. I think it's more recognize the fact that if you plug in 1/2 into here, you do get 1/2 over 3, you get 1/2 for this, 1/2 to the 5th power over 7. And the approximation for the first two terms is just 17 out of 120. But I guess if you were to subtract the true with the approximation, you can kind of get rid of the first two terms. So really, you kind of just focus on this term. You're plugging 1/2 in, and you want to see it's less than 1 out of 200. I think that's what they're doing there. So we'll probably do a little more practical error bounds, because I know we're about to run out of time. The last thing I want to talk about with you guys is L'Hopital's rule. That's a 2013 exam, because that could show up. Now, hopefully you guys remember L'Hopital's rule. L'Hopital's rule will apply you get 0 over 0. Because, for example, if I were to plug in f of 0 plus 1 over sine of 0, f of 0 equals -1. You do get 0, 0. So what you're going to do then is take the derivative of the top and derivative of the bottom. If you do that correctly, you get f prime of x over cos x. Now it's going to be f prime of 0 over cos of 0. F prime of 0, we kind of worked out earlier, is going to be -1 squared times 2 times 0 plus 2 over cos 0, which is 1. -1 squared is 1 times 2, so you just get 2 straight up. So you could see that. They've actually had some creative ways of doing L'Hopital's rule in the last couple of years, so we'll look at that as well. Yeah, let me just pull up the answer really quickly so you see how they score that. Yeah, you first have to verify that you're doing the L'Hopital's rule. And then you kind of show it and you get the answer. So that's how it works out. So yeah, we did a good amount of work with Taylor's series. Hopefully that you guys are comfortable with that. We did Euler's method. Hopefully you're comfortable with that. We did look at some Maclaurin series problems. I do need to spend a little more time with the error stuff, because I need to make sure I give you a little more practice with that. We did talk about the ratio test and how to write the general term. We did do elliptic toast. We did some of the kind of things a little bit more BC specific questions. What I imagine I'd want to do for Friday, it could be a hodgepodge. I mean, we could do related rates, we could do volume, we could do differential equations. I think I'll probably do differential equations, like number 5C, I think is good. And then maybe do a little more practice with that. Then maybe another Friday we do volume, another Friday we do related rates. Related rates are not showing up too often, so I don't know if I'm going to spend too much time with that. But I just want to make sure you guys are fully prepared. So I want to, I know if as a betting man, I'm saying it's FTC and series. That's what's going to be the BC exam, but you never know. They could throw you a curveball, or they might have like a small part of one of the questions that might involve related rates, might involve differential equation, might involve volume. You don't know. So we'll see. So yeah, and then we'll go back to 4 o'clock. I do have a virtual memorial service to attend right now. So yeah, so we'll do this again, and I'll send the recording of this video, and yeah, we'll just keep doing this. So any questions at all before we sign off? Nope? Okay, cool. All right, I will see you guys later. All right, have a good one.
Thank you.
Thank you.
Thank you.
Bye.